Hi, I'm Filip Aronshtein.
I'm Peter Weiss.
And these are our diode circuits. Right here we have our first diode circuit. We have our VC connected to the one pole of our diode. So diode VN. But yeah, we have VN connected to our, VCC, whatever. We have our VN connected to our diode, which is fed into a 1 kilo ohm resistor, which is fed into ground. Here is our second circuit. Huh? Oh yeah, here's our second circuit.
In the first circuit, we measure the voltage across the resistor and the input voltage.
Yeah. So here we have the same sort of situation, except the diode feeds into a capacitor and a 10 kilo ohm resistor, which are connected in series to ground.
In parallel.
In parallel. I always mix them up. In parallel to ground. And we measure the resistance across...
The voltage across the resistor.
The voltage across the resistor. And that gives us our V out.
And we measure V in, and we do it with and without the capacitor.
Yeah. But this is our passive half-wave. This is a passive half-wave rectifier. And over here we have an active half-wave rectifier.
Yeah.
We have an active half-wave rectifier using an op-amp. So we have the op-amp, we have the negative V in connected to the V. We have our signal coming into our positive V in, and our 10 kilo ohm resistor going to ground. Then our output of our op-amp goes through the diode and back into V in, the negative V in.
Yeah, so the signal goes into the non-inverting input, and the feedback loop from the diode goes back from the output to the inverting input, and the resistor gets connected from the inverting input to ground.
Yep, and this is being powered by the op-amp is being given plus or minus 5 volts here and here.
From the power rail.
Yeah, from the power rail to the left and right.
We switch these purple wire and black wire to the power rail for this second circuit because we use the power rail for VN and we need an AC signal. And then we have, so for part one, we have the IV curve for the diode. Notice that when the voltage is low for the voltage across the diode, we don't get any current really and we don't get really any current until we get to around like 0.6 volts, maybe around 0.7. And from there you can see that the IV curve is roughly, it grows, and we have current across the diode when the voltage is high enough.
It opens up and it becomes linear once we cross the threshold. Well, the relationship. Well, we see the diode acting like an open circuit.
Yeah,
as close to an open circuit as possible.
Not open. We see the diode acting as like a short circuit. We have current passing through the diode, and it's like an exponential relationship here. If we increase the voltage even more, the current would probably be much higher. But we get a roughly constant voltage drop, so like the voltage is not going to go too much higher. But this is what the IV curve that we should see for the diode. We don't get current until we get to a certain threshold voltage, which is around like somewhere between 0.5 and 0.7 here, maybe around 0.6. And then we have the waveforms for part 2. So this is when we used 5 volts input to the passive half-wave rectifier, and you see that there's a little voltage drop from the input to the output, and you only see the output voltage though when the input is positive, because that's what half-wave rectifier only rectifies half of the wave. And then we have, this is the same thing, and this was without the capacitor, so there's no sort of, there's no, what's it called, ripple. And now here with the capacitor, we see this ripple here, and the max voltage is about the same, but it stays roughly constant because of the capacitor, except with a little ripple voltage. And we can measure that ripple voltage with the cursors, which is what we did here, and the ripple voltage is around 1.787 minus 1.644, so that's maybe around 0.14 volts for the ripple voltage, peak to peak. And we can do the same thing now with an input voltage of 2 volts peak to peak. And because of that, we see that the voltage drop from input to output is much more pronounced, and the output is very low because the input voltage is pretty low. And remember, we have to get to a certain threshold voltage to even have an output at all. And this is without the capacitor. And now this is the active circuit, the active half-wave rectifier. And now we see the voltages match exactly because we have power to do it actively. So it rectifies the half-wave without any voltage drop. And that's at 1 volt amplitude, so 2 volt peak to peak, and it's perfect. And we have no voltage drop, only half-wave rectification, and we can even decrease it to 0.5 volts amplitude, 1 volt peak to peak. And before, we wouldn't have any output for this with the passive because it has to be above around 0.7 volts or maybe like 0.6 or 0.5 volts to have any output voltage at all. But here the output voltage still matches perfectly with a 0.5 volt amplitude because we have power, because it's active. And these two were at 1 kilohertz. But when we switch to 10 kilohertz, it's very similar. It's also 0.5 volt amplitude, except we have a little distortion in the output here. The output doesn't quite get to the input until a while in, and that's because of the slew rate of the op amp. And we measured the slew rate using the cursors here, and you can see the slew rate, delta y over delta x, is around 0.26 volts per microsecond. So about 0.26 volts per microsecond, which is about the same as the slew rate for the op amp that we measured in previous labs. Okay, thank you.